Hello everyone.
Hello, sir.
So welcome to week 4 live session of Semiconductor device modeling and simulation. I am Om Maheshwari and today we'll discuss some questions that may help you in your assignments as well as your exams. So in this week we will mainly talk about the PN junction under equilibrium, derivation of the IV equation, multi-carrier diffusion equation, non-idealities in the PN diode, breakdown, generation, recombination currents, and some transistor configuration or a very brief introduction to BJT. So I hope you have seen the videos of this week. So that will help you in your assignments. And I'll talk about some questions now. Let's start. So in this first question, we have an abrupt PN junction. The doping concentration on N side is 10 to power 10 to power 16 per centimeter cube and P side is 9 into 10 to power 16 per centimeter cube. Assuming PN junction is reverse biased, the total depletion width is 3 micrometer. Calculate the width on the P side. Please try to attempt this question. Then we'll solve it together. Did you reach an answer?
Sir, please wait for 1 minute.
Okay, sure.
It is point. It is point 0.3 micrometers, sir.
Yeah. Okay. So let me just show it for the recording sake. So we have a PN junction. This is P side. This is N side. And we would have some depletion on both the sides, let's say. And let me call it, let's say this is 0, this is xn, this is xp. So this xp is the depletion on the p side, and this xn is the depletion on the n side. So if we know by charge neutrality, NaXP equals to NdXn, right? This is a very important equation to remember. This is always true in PN junction. So, and we also know the depletion with total depletion with WD is Xn plus Xp. So what we have to find is we have to determine calculate the depletion width on P side. That is, we have to find Xp. Okay. So if we replace, we know here this WD is 3 micrometer. It is given here. P micrometer is Xn plus Xp. So if we replace this Xn in terms of Xp, we can find what Xp is. So let's try to find out from here. Xn is NaXp upon Nd. We put the values of Na and Nd. Na is 9 into 10 to the power 6, 16. Nd is 10 to the power 16. And Xp, this gives me Xn is, this 10 to the power 16 will cancel, this is 9Xp. And if I substitute it here, then 3 micrometer equals to 9Xp plus Xp. 3 micrometer is 10 XP. XP is 0.3 micrometer. Is this clear?
Yes, sir.
Yeah. Did you use the same approach or were you doing something else?
No, sir. Based on charge neutrality, sir.
Okay, great. So let's see the next one then. At 300 Kelvin, a diode current of 1 milliampere flows through a certain germanium diode that requires a forward bias of 0.1435 volts, whereas a silicon diode requires a forward bias of 0.718 to flow the same 1 microampere current. Sorry, 1 milliampere current. Find the ratio of the reverse saturation current for germanium and silicon. And this is the ideality factor for silicon is 2, for germanium is 1. Value of Kt is given to be 25.9 millielectron volts. Just try to conceptualize the approach, then we'll solve this. Let's see how to solve this one. Okay, so we know that the current in the diode is I equals to I naught. I naught is the reverse saturation current, e to the power V forward bias voltage by eta Vt minus 1. Okay, so we know that this current is 1 micrometer that is flowing through, sorry, 1 milliampere that is flowing through both the germanium and the silicon diodes. And this, the condition that is given in the question is I naught, let's say for germanium, is e to the power, the forward bias voltage is 0.1435 divided by eta Vt. Eta is 1. Vt is, let's say, is 25.9 milli electron volt, 0.0259 minus 1 equals to I naught silicon e to the power 0.718 upon 2 into 0.0259 minus 1. Okay, what we have to find is I naught G, and both of these are equal to 1 milliampere. What you have to find is I naught G upon I naught Si, the reverse ratio of the reverse saturation current for germanium and silicon. So if I write this will be in the numerator and this will be in the denominator. E to power 0.1435 by 0.718 divided by 2 into 0.0259 minus 1 upon 1435 divided by 0.0259 minus 1. So it will be something e to the power 13.861 upon e to the power 5.54. This one we can ignore because e to the power 13 and e to the power 5 are much larger numbers than uh, this minus 1. So when I solve this, it will come out to be 4.1 into 10 to the power 3. This I0 GE by I0 SI.
Sir,
Yeah.
uh, um, okay, sir. Okay, 2 into 0.2. Okay, sir. Okay, no issue.
So these ideality factors are given, right? Take those in consideration. This is for silicon. This is for germanium. Okay, so let's see the next one.
Sir, 1 minute, 1 minute, sir.
Yeah, sure, no issues.
Okay, sir.
Okay. So next is a very simple question. Which of the following represents the band diagram of the below device under zero bias? So we have N plus, N, and P. So what would be the answer?
Sir, would it be, na?
B is incorrect. See it carefully. It is N plus N and P.
Sir, C, sir.
No, it's A. Okay, let's see
Why,
this.
sir? Why,
Yeah,
sir?
yeah. So what we have is N plus N and P. Okay, so what do you know about N plus? N plus means that EF will be very, very close to EC, right? This is N-type behavior, N
Yes,
plus.
sir.
In N-type also, EF will be closer to EC, but not as close as N plus, but it will definitely be above EI, right? EF will be somewhere between EI and EC. This is N-type. This is N plus. Is this clear? Okay, please feel free to stop me wherever you feel you don't understand. P-type. In P-type, what do we have? EC, EV, EI. In P-type, Fermi level is between EI and EV, somewhere here, right?
Yes, sir. Yes, sir.
Yeah. So if you see all these cases, this is here, this is EF, right? In equilibrium, EF is constant. So if I take a constant equilibrium, EF will be constant. So this will be N plus, this will be N type somewhere like this, and this will be P type where EV is close to EF. Right. So this is how your Venn diagram would look like. N plus N and P. Is this clear?
Yes, sir. Yes, sir.
Yeah.
Actually, sir, hello.
Yeah.
Sir, actually, sir, means in case of N type, the conduction band near the Fermi level, and in case of P type, the uh, valence band near the Fermi level.
Yes. Yeah.
Okay, sir.
So what Fermi level tells you is probability of finding electrons, right? So in N type, there is higher probability of finding electrons in the conduction band. Whereas in p-type, we do not find electrons in conduction band. All the electrons are bonded in EV, in the valence band,
EV,
right? Yeah,
EV.
yeah. So, okay. So just keep in mind where in n-type behavior is where EF is close to EC, p-type behavior is where EF is close to EV.
Okay, sir. Okay,
Yeah,
sir.
yeah,
Wait for some time, sir.
sure. N plus N and P.
Okay, sir.
Okay, so if this is clear, can you tell me what kind of device is in B? What is this NP, N or P? Which is this N or P? What is this?
Sir, in second, first is P,
Right.
second is sir N,
Yeah.
and third is P plus, sir.
Okay. Very good. And then the last one,
Last one, sir. First one is sir N plus,
N plus.
P,
Yeah.
P plus.
Right. Okay. So I hope this is clear now.
Yes, sir. Yes, yes.
Okay. So let's see the next question then. The question is, calculate the built-in potential VBI for a PN diode from its electric field profile as shown below. So just attempt this question.
Okay, sir. I try one.
Just think about the approach, then we'll solve it.
Sir,
Yeah. Yes.
sir, it can be do by KT by Q into ln, Na into Nd by Ni square.
Yeah, that is built-in potential, but do you know NA and ND here?
Not given here, sir.
Okay. Can you calculate it from the information given?
Try, sir. Try,
Okay. So let's not go that way. It is like you can do it that way also. We'll discuss that, but let's see the easier way first. Okay. So so what do you know? So do you know the derivation of this p-n junction electric field?
no, sir.
Okay. So I think it is there in the videos. I recommend you see that. So I think it will be not good for our time if I go into the entire derivation, but I recommend you just follow through it somewhere from the internet. Then this question will be much more clear to you. So basically, what is simply voltage? Voltage is E dot. dx, right? Or
Yes.
in this case, it will be the integration of E dot dx. Okay. So basically, VBI is nothing but this integration is nothing. We have this x versus E. So this is area under the curve. The area under this curve is simply your VBI, built-in potential. So that is true for any NP or PN junction. So keep that in mind. The area of the electric field tells us VBI. So to simply calculate the area will be, this is a triangle, right? Half into base into height. Base is 1.3 micrometer. This
Yes,
height
yes,
is
sir. Yes.
10 to the power 4 volt per centimeter. 1.3, I'll keep everything in centimeter. 1.3 into 10 to the power 4, and height is 10 to the power, sorry, 10 to the minus 4, and height is 10 to the power 4. This will come out to be 0.65 volts, which is 650 millivolt.
60 millivolt.
Yeah, this is VBA. Now, like this is definitely the easier way, but yeah, the question could be, if you are given this profile, this electric field profile, if you are given, can you find Na and Nd? That is also a good question, and yes, we can find that. So actually, if we if we this peak point in the this 10 to the power 4 value, this is actually equal to, this value is equal to uh, Q Na xp by epsilon, which is also equal to Q Nd xn by epsilon. So this epsilon is the permittivity of the silicon material. Q is the charge. NaXp. If let's say this is in this case, I think, and let's take any one of them. Let's say this is Xn, this is Xp. So Xn will be zero point 0.3, Xp will be 1. This is 0, right? So if you substitute all this, you can find Na and Nd also. You need know this is equal to 10 to the power 4. Xn you know, Q you know, epsilon you know, Nd you can find. Similarly, you can find Na also. Is this clear?
Yes, sir. Yes, sir. From that, I can apply the formula, na?
Yeah, then you can apply VBA formula, but that's not required. You can directly calculate the area. That's the easier way. We need to look for the
Yes, yes,
simplest
yes.
cases, right? And this is also where the charge neutrality comes from, right? While deriving the electric field, this condition comes. Then only we can say NAXP equals to NDXN. This is the charge neutrality condition. So I highly recommend you look at the derivation of the electric field.
NDXN होगा ना?
Yeah, sorry, NDXN. So I highly recommend you look at the derivation. It will help you a lot. Okay, so let's see the next one then. Is this clear?
Yes, sir. Yes, yes, clear.
B is the answer. Okay. Let's check this question at the end. This is about BJT, and I don't want to confuse you right now. Let's take this question first. Please read and try to attempt this question. It's a simple one again.
Sir, if the answer is 4 micrometer,
Let's see how to solve this question. So if you know WD, how do we calculate WD is 2 epsilon VBI plus VR. This is the reverse bias voltage upon Q, Na plus Nd upon NaNd. The depletion bit under the influence of reverse bias voltage VR. So we are given that 2 micrometer is equals to 2 epsilon by Q. VBI is 0.8 and VR is 1.2 plus Na plus Nd upon NaNd. In the second case, let's say WD2 that we have to find 2 epsilon by Q, zero point 0.8 plus this 7.2 volts of reverse bias. Rest everything is same. Let's say this is 1, this is 2. So I simply take do equation 2 by 1. What I will get is WD2 by 2 micrometer equals to under root. This will be 8 by, let me write it like this only, zero point 0.8 plus 7.2 upon 0 0.8 plus 1.2. Rest everything will cancel out, and this is equals to under root 8 by 2, which is WD2 is 2 micrometer into under root 4, which is 2 micrometer into 2, 4 micrometers. So at 7.2 volts, the depletion rate will be 4 micrometer. So I hope this question is clear to all.
sir, wait, sir.
Sure. Did you use some other method to find it?
Sir,
Did you find it in the same way?
no, sir. Actually, we can calculate this by deflection ratio.
Okay. How do you know the depletion ratio?
Sir, there will be given that, sir, 0.8 is the built-in potential.
Hmm.
0.8 is the built-in potential, sir,
Yeah.
and there will be point 1.2 and 7.2 are the applied reverse bias voltage.
Yeah.
So into the depletion of the second and first ratio.
Okay, we have done the same thing, right?
Yes, yes, sir, yes.
Yeah. See here. I just expanded the formulas because you should know where it is coming from, right?
Yes, yes, sir, yes, sir, yes, sir.
So if someone asks you to calculate the entire, if they have not given something else and ask you to calculate depletion width just by giving this number, then you can calculate it also if you know NA and ND.
Yes, sir, yes, yes.
Okay, can we go to the next question?
Wait, sir, wait, wait, sir.
Okay.
Okay, sir. Okay.
Okay. So look at this question.
Sir, if the answer is 0.22,
Yes, the answer is 0.22 volts.
but sir, it is electron volt, na?
No, this is volts. It's built-in potential, right? Potential will be in volts.
Okay, 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 sir.
Okay, so let's see this. So we are given the resistivity of germanium diode. On P side is 2 ohm centimeter and N side is 1 ohm centimeter. You have to calculate the built-in potential. So rho n N side doping, N side uh, resistivity is, or I can write 1 by sigma n, which is 1 upon nq mu, 1 upon nd q mu n. This value is equal to 1 ohm centimeter. Similarly, rho p is 1 upon sigma p, p q mu p, naq mu p, which is 2 ohm centimeter. So I have to find here nd and na. So if I just substitute the values, NdQ mu n is 1 equals to 1. I'll skip the units for now. NaQ mu p is 1 by 2. So Nd will be 1 upon Q mu n, which is 1.1 upon 1.6 into 10 to the power minus 19 into 3800. And if I solve this, Nd will be 1.644 to 10 to the power 15 per centimeter cube. Na will be 1 upon 2 q mu p, which is 1 by 2.6 into 10 to the power minus 19 into mu p is 1800. This will be equal to 1.736 into 10 to the power 15 per centimeter cube. Now we know VBI is KT by Q ln Na and D by Ni square. KT by Q I assume it to be 0.026 volts or 26 millivolts. Ln 1.736 into 1.644 to 10 to the power 15 into 10 to the power 15 divided by Ni square. Ni value is 2.5 into 10 to the power 13. 2.5 into 2.5 into 10 to the power 13. Okay. So if I solve this, I will get is VBI is 0.291 or 0.219, I think 219, which is equal to 0.22, which is the answer, option C. Is this clear?
Yes, sir. Yes, sir. Wait for some time, sir.
Sure.
Okay, sir.
Okay. So this is the next question. Please try to answer this. Theoretical.
Sir, is this D, sir?
Which? Sorry, which one did you say?
D, sir.
B.
D, sir. Delhi.
No. Okay, so let's not waste time. It's a theoretical question. It is option A. Okay, so let's see why. So so what it means is the temperature coefficient of avalanche breakdown voltage is positive. What does this mean is as temperature increase, the breakdown voltage in avalanche increase. Okay, so so to understand this, we need to know what is avalanche breakdown. Okay, so have you seen the video for avalanche breakdown?
No, sir, not you.
Okay, so let me explain very briefly. Okay, so both of these breakdowns, avalanche or xenon, they happen in reverse bias conditions. Okay, so we have to do breakdown. What we have is a pre-n junction diode. P, this is N, and let's say this is reverse biased. VR. Okay, so if I draw the band diagram, it's something like this in the reverse bias. Yes, call it EFN, EFP. Okay, EFP will be near EP. This is N side, this is P side. Okay, so what happens is in reverse bias, so this will be your applied reverse bias VR. Okay, it would actually be oh, fine. Here. Okay, so what happens in this reverse bias? The electrons, the magnetic carriers in the p-type conduction band. They gain a lot of energy, and what they do is, as they move, they lose some energy to the lattice, and they generate electron-hole pairs in this depletion region. There's this depletion region here. They strike with with the atoms in the lattice, and they generate more electrons and hole pairs. So holes. Uh, so now this electron already was there. Now this electron further it strikes with it strikes with the lattice to generate more electrons and holes pairs. So this is how the avalanche breakdown takes place. Like the electrons are the excited electrons under the reverse bias. They strike with the different atoms in the lattice and generate more electron hole pairs, which further accelerate and generate more electron hole pairs. So that's how breakdown happens, and the current suddenly increases in the reverse bias. So that is avalanche breakdown. So so what happens in avalanche breakdown when we increase the temperature? So when you increase the temperature, um, as you increase the temperature, what will happen is the vibrations in the lattice will increase. The vibrations will increase, which means phonons increase, and these phonons scatter the electrons. Right. So what will happen is the electron scattering increases. And what does this mean? When electron scattering increase means electrons lose energy. And if electrons are losing energy, uh, that means the electrons here which were going to strike somewhere and generate more electron hole pairs, they are decelerating. They are losing their energy. So there is less energy with an electron to transfer to the lattice. Or to generate more electron hole pair, there is less energy with the electron. So thus, to 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 get the breakdown, you need to apply more VBR. So as temperature increases, your breakdown voltage increases. So this is the positive coefficient. Mm,
Sir,
yeah,
if the temperature increase, vibration increase, and electron scattering also increase,
yeah.
then sir, one time more.
So what is phonon scattering is okay. So your lattice is nothing but like a systematic arrangement of different, let's say, silicon atoms, right?
Yes, sir. Yes.
And electron is traveling somewhere in its electron cloud above these atoms. Okay. So now what happens is when your electrons, when you increase the temperature, these silicon atoms are vibrating on their place, right? They are going left and right, top and bottom, like they're vibrating. So what does this mean is, uh, let's say with an analogy we can think about it. The electron that had to like go through the smooth road is now going through a very rough road that you can like take a analogy here. Like when these atoms are vibrating, the motion of the electron is hindered further. So this is what phonon scattering is in a very layman term. So does this make sense to you, or do you want me
Yes,
to?
sir.
Okay.
Yes.
So this is what phonon scattering is, and when temperature increases, the scattering increases. That means electrons are losing energy as they are traveling forward, right? So they are losing energy as they are traveling forward. And they're losing energy, they have less energy to strike to some atom and generate more electron hole pairs. So we need to apply more VBR to generate those electron hole pairs. That means as temperature increases, your breakdown voltage increases. Okay.
Okay, sir.
Okay. So there's one more thing associated with this question. It's not asked in this question, but I want you to look into it. The temperature coefficient of Zener breakdown is actually negative. Okay. So I want you to like just read about it. What is Zener breakdown? How is it different from the avalanche breakdown? And why its temperature coefficient is negative? So look into it. If you don't get the answer, we can talk about it in the next class. Okay. So both of these concepts are very important when you're studying devices. So you should know both of them thoroughly. I just explained very basics of avalanche breakdown, but look into what is linear breakdown, how is it different from avalanche breakdown, and why its temperature coefficient is negative. Okay.
Okay, sir.
Okay, let's see the next question then. So again, a very simple question.
Sir, option C, sir.
Yeah, option C is correct. So this is P10. So in N-type, it has donor atoms which donate electron to become positively charged. In P-type, we have acceptor atoms which take electron to become negatively charged. So immobile positive charge is on N side, right? Okay, so this was simple question. Let's see next one. Just read about this one and try to attempt it. Yeah, so we have solved a similar question before also. So this
Sir,
should not
wait.
be. Yeah.
Okay, sir.
Did you get the answer? Did you get the answer? Okay. Anyways, let me solve it. So at zero bias, depletion with WD is under root 2 epsilon EBI by Q Na plus Nd upon Na and D. So all these values are given. So if you have to 2 into 11.7 into 8.854 into 10 to the power minus 14. We'll take minus 14 when we have to find it in centimeters. Upon Q will be 1.6 into 10 to the power minus 19. Na is 10 to the power 16 plus 5 into 10 to the power 15 upon 16 into 5 into 10 to the power 15. So now we just need to do the sum calculations. We solve it, it comes out to be under root 719 minus 9, which is 5.214 into 10 to the power minus 5 centimeter, which is 0.5214 into 10 to the power minus 4 centimeter, which is 0.5214 micrometer. This is option B. This is clear. It is pretty straightforward and formula based. There is no twist in this question.
Yes, sir. Yes, sir.
Okay, can we move to the next one? Okay, so let's go to the next question then.
Yes, sir.
Again, a Venn diagram based question. So,
That this is, I think, sir, option D, sir.
correct. D is correct. This is T, this is I, and this is N. What is A? What is the
NIP, sir. NIP.
yeah, NIP? And what is this one? B?
C or B, sir.
B?
B is, sir, INP.
C
C is, sir, NIP.
is
Sorry,
NIN.
NIN. Sorry, sir. Sorry, sir.
Okay, so now you know how to do this. Uh, Next question. So next is very basic question. So this was from your
C.
current
Option C,
assignment.
option C, option C.
Yeah, you can simply calculate it. KT, just by multiplying KT, you will get the answer. Okay, so this question, let's take this one. Can you guess the answer here?
Sir, C, sir, option C.
No, it is option A.
Option A, sir.
Okay, so what happens in Zener diode is your both of the N and P junctions are very highly doped. It is like N
Highly
plus,
doped, sir.
let me draw it, P plus and N plus. So there is very thin depletion width on both the sides. And when you apply a large reverse bias, VR, what happens is You get a very thin, this is a very thin depletion width. So you get some this kind of band diagram. This is N plus side, this is P plus side. So what happens is electrons that are there in the valence band, they tunnel through this barrier, depletion barrier, and go to the N side. This is the principle of Zener breakdown, or that is how Zener diode works. Okay, so I hope this is clear.
Okay, sir.
Next one.
Sir, option A, sir.
Yeah. Depletion capacity increase with increase in reverse bias. Okay, let's see this. So you have a PN junction diode. So both have some depletion on some side. Let me call it WD. And we are applying some reverse bias. Okay. So can you tell me when I am increasing reverse bias, what is happening to WD? Is it increasing or decreasing?
Sir, if I increase the reverse bias,
Yeah.
with increase, sir.
Okay. Depletion width will increase. So what would happen to the capacitance? It will increase
Capacity
or
also increase, sir.
no? Capacitance will
Oh, capacity
decrease.
decrease. Sorry, capacity decrease. Sorry, decrease,
Capacitance
sir.
is epsilon A by D, or
Ah,
WD
it's
is
not
come
able.
in the, so if this is increasing, this will decrease.
So option B is there, sir. Option
Yeah,
B is there.
option B is correct.
Okay.
Okay, so one more question I have. Yeah, this one.
P2N, sir. B, sir. B.
No, that's incorrect. Again, in P-type we have negative ions, right?
Yes.
And in N-type we
Oh,
have
oh,
positive.
oh. Achha. Only deflection with, sir. Oh, okay, okay, sir. It is N2P, sir. N2P. Sorry.
So electric field will flow from positive to negative inside the depletion
No,
layer.
actually, sir, I can say that whole device.
The whole device, that will happen if you're applying a forward bias or reverse bias. That will
Yes.
depend on that, right?
Okay, okay.
Yeah. So what forward bias does is when you are applying like this, it is basically negating this depletion electric field only, right? See applied built in.
Yes, sir. Yes.
Okay. So it is from N to P.
N2P, N2P, sir.
Okay. So let me go back to those BJT questions that we left. Mm, let's see this one first. So okay, it may be possible you don't know what a BJT is. So let me just quickly tell in a very brief way. BJT is a device that has three terminals, and it is basically a combination of different NP junctions. We have an emitter, we have a base, we have a collector. Let's say we are talking about an NPN BJT. There are two types of BJT, NPN and PNP. Let's take this one. Let's say this is an NPN BJT. So this will be emitter will be N plus. Actually, it will be very heavily doped. Base will be P. Collector will be N type. So emitter is always very heavily doped. So now, and both base and
I think,
collector are moderately doped. So with this information, can you answer the question?
sir, is this the B emitter, base emitter will be greater compared to base collector?
Right. See option D. Because we know that, right? VDI is KT by Q ln Na and D by Ni square. So Na is same. Let's just talk about this junction or this junction. For both of them, Na is this base doping. But Nd for emitter is very high, whereas
Yes,
for
sir.
collector it is low. So VBI for base emitter will be higher than VBI for base collector. Okay, this is a simple question. Okay, let's see the next one. So this is the last question I have for today. Can you comment on this one?
So I think uh, beta equal to IC by IB.
Okay, equals to IC by IB, right?
Okay. Now activation according collector is reverse bias base collector, reverse bias voltage at
So
base collector.
let me give you some more background so you can answer this. We have, let's say, the BJT and plus PN, this emitter base collector. So in the active region, they say it is an operating in active region. In active region, we forward bias here, is forward bias the emitter base junction, and we reverse bias the base collector junction. So this is reverse bias. So this is VCB, this is VB. Now you have to tell when they are increasing VCB. Will this beta increase or decrease?
Sir, GCB increase when beta increase
Okay, why?
because sir, VCB means IC into RC.
What is RC?
RC means collector resistance.
Okay,
And sir, if I consider that collector resistance is some constant value, so as the V increase, sir, IC also increase. So beta also increase, sir.
okay. Uh, Actually, no. You see, if I draw IC versus VC,
Sorry, sir. Sorry, sir. Sir, actually, sir, you put VC reverse bias, na?
yeah,
Then, sir, in case of reverse bias, if we increase the reverse bias, the current will be decrease.
okay. So let's think about it a bit. This is how IC will look like. IC whatever you call it.
This is the output characteristic, na, sir?
Yes, this is output characteristics. So in output characteristics, let's say this is saturation, this is the active region. In the active region, when you are increasing VC, IC does not increase ideally.
Yes, 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 sir, yes, sir. So beta remain constant, na?
Yeah, beta can remain constant, or if we talk about a non-ideal device, then beta will increase. But how that will increase, the reason is what you gave is not correct actually. So definitely IC will increase, then only beta will increase. But how we understand this, you can understand it like this. Okay, let's look into the device. So you have some depletion width on both the sides. When you are increasing VCB, what would happen is this depletion width would increase, right?
Increase, sir.
So there will be some depletion here also. Okay, so basically, let's say your base width is TB. So when you are increasing VCB, your base width is actual neutral base width is decreasing, right?
Decreasing, sir. Yes.
So if you know IC is proportional to 1 upon TB and your IB is proportional to directly to TB. So both
Yes,
your
sir.
IC is decreasing and IB is increasing. So your beta will increase. Now
Sir, what this
to
is?
understand
This is a factor.
what?
Sir, this is a, actually, sir, the change of IC will be more compared to IB, na?
Yeah, yeah, that's true. Uh, I don't know.
Actually,
I I need to check that. I'm not sure if change in
no,
IB
no, sir.
IC will.
Actually, number of sir, IC depend upon the number of carriers available in case of collector.
Yeah, IB is definitely much less than
So in that
IC.
case, sir, how sir? Okay, sir. Okay. In that case, sir, beta how sir increase, sir? Okay, okay. No, this is confirmed, sir. Okay.
Okay, I think I drawn it incorrect way. IC will decrease. This is correct, right?
These are
TB is
correct. These
decreasing.
correct. Yes, sir. This correct, sir. This correct.
Yeah, sorry, it was my mistake. But
No, no, sir. See.
yeah, yeah. But to understand this, like this, you need to understand where IC comes from. So I don't know if it was there in this week's video, but look into it. Basically, IC, the current actually depends on how many electrons are coming, how the electrons are diffusing into the this from the emitter to base. And this diffusion current IEN is inversely proportional to TB. And these electrons just which are there in this, which are coming from this forward bias emitter into the base, they just diffuse to this junction, and then due to this reverse bias here in the depletion region, they go into IC and they constitute the most part of IC. IC, the maximum portion is IEN itself. So that's how this dependence comes of 1 by TB. Whereas why base current increases as TB increases is uh,
Hello, sir. 1 minute.
yeah,
Sir, is this course helpful for embedded systems like that?
sorry,
Is this course, sir,
yeah.
is this helpful for embedded systems like that when it add on to that field or that domain?
See, this is a very basic devices course. I don't think it is important for uh, any of the domain in related to electronics engineering, and embedded is related to that. So I think the basic devices are very necessary to understand for anyone in related to electronics.
Device modeling and on like what would be the use
So
like
okay,
semiconductor device
so
modeling?
so okay, you may not be like doing the modeling on your own, right? That's true, but here we are just discussing the basic physics, right? So that will definitely be helpful to you when you are working on some larger circuits or at some larger scale on some uh, whatever electronics you work on. There, the building blocks are definitely these transistors, resistors, capacitors itself, right?
Yes,
So
sir. Okay, sir.
I don't know like how they will directly help you, but you will definitely have an edge if you know these details, what's happening actually happening inside the devices. Okay, so what I
Sir,
was telling is how why is IB proportional to TB? So basically what IB is, electrons are coming from here and holes that are there in the base, they recombine with these electrons, which basically make IB. So if there is a larger base width, there are more holes, and there will be more IBs. So that's why IB is directly proportional to TB.
But sir, hello.
Yeah,
But sir, uh, here you write that IB, so obviously IB is focused on TB.
yeah.
But if the sir VB we can change. If we increase the VB, then also sir IE will be increased, which can also create the recombination is large.
If we increase VBE, this,
Then the amount of IE also increase,
okay, yeah,
and if IE increase, sir, then
I,
also the amount of electron also enter to the base region is more.
yeah.
So there will be also, sir, means it is depend upon the amount of VB increase, sir.
Okay, yeah, definitely. So when you are increasing VB, you're actually your beta also increases to a certain extent and then starts to fall. But let's not get into that right now. It will be confusing. But uh, yeah, you are right. So if you are increasing VB, more
Hmm.
electrons will go from here. And actually, this injection is proportional to e to the power VB, right? If you remember
Yes,
your
sir.
PN
Yes, sir.
junction,
Yes, sir.
VB by eta VT.
Eta
So
VT.
yeah, so exponential there's an exponential dependence on this diffusion or on this injection of electrons, whereas this recombination current is not exponentially dependent on VB. The recombination that is happening between to constitute into this IB is not exponentially dependent on VB.
Okay, sir. Okay.
Let me see if I have those formulas somewhere. I can write them for you. Okay, so I don't have the formulas right now with me. Maybe uh, try to look for it or see it in the videos. I think there it is there in the videos. And if you still have doubt, I think the next assignment will also be on BJT. We'll discuss it in detail in the next assignment.
Sir, is this is next week, sir?
Yeah, in week 5 assignment, I think there are more questions on BJT. Week 5 videos are all based on BJT.
Okay, sir. Sir, I just want to ask you, sir, one question, sir.
Yeah,
The every video are 30 to 40 minutes, sir, and I think 5 videos are there.
yeah.
It requires, sir, lots of means time requires, sir.
Okay, okay, so like it is a very fundamental course, right? And it requires you to like it will demand your time. So there's no other way. You can watch it at 2x if you understand it quickly, but if not, you will have to watch it.
Okay, sir. Okay.
So it is a
Thank
one-time
you, sir.
effort. If you understand it like in the first go, you don't have to like read it again and again throughout your like whatever work you will be
Yes.
doing in the future. So spend this time and learn it properly, understand the things. So it will not be a waste. So just think it
Thank you, sir.
that
Thank
way.
you.
Okay, so I don't have any more questions. So we can close the session now. I will upload the video as well as the slides on
Sir,
the Google Sheet.
you can again take the classes next Monday, na?
Yeah, I'll take the class every Monday.
Okay, okay, okay.
Yeah.
Sir, if any doubts are there uh, from the
You can
previous lecture,
you can email me. Any doubts, you can email me.
okay, okay, sir. Thank you, sir.
Okay, thank you.